So when we're adding and subtracting radical expressions, we're essentially just adding and subtracting like terms. You know that 2x plus 5x is 7x. You know that 2x plus 3y just can't be done. It stays at 2x plus 3y. So in the same way, if we have the same radicand, that's the number underneath, and also the same index, right? Square roots with square roots, cube roots with cube roots, we are allowed to add them together. But that doesn't change, right? 2x plus 5x is still 7x. So 6 times the square root of 7 plus 4 times the square root of 7 is still 10 times the square root of 7. Only that coefficient is changing. So when I see something like this first example, my brain is basically seeing 6y plus 3y minus y, which would just be 8y. Just in this instance, it's 8 of something else. Instead of 8y, it's 8 fifth roots of 4x. So when they had that fifth root in common, as well as the radicand of a 4x, they were able to be combined. These two can be combined. They are both cube roots of 2. So is the other one, but we'll get there in just a second. This one for sure, 1 plus 5 is 6 cube roots of 2. And we do have the same radicand of a 2 and index of 3. But the coefficients aren't actually something that we can add because our coefficients aren't like terms. But what we can do is say, well, their coefficient would be 6 minus 7x, whatever that happens to be, because they have the same index and radicand. Sometimes things look like they can't be simplified or combined because square roots of 8 and square roots of 2 don't have the same radicand. But the square root of 8 isn't fully simplified. The square root of 8 is, let's see, we gained a 2, so 3 times 2, and then we had our square root of 2. And then they are actually combinable. And sometimes they just won't be. Square roots of 5 can't be simplified, square roots of 3 can't be simplified, so we cannot combine those unlike terms. So these look unlike, but I at least notice out of my first term that I can do some simplifying. The cube root, see, I'm going to leave myself a space there. The cube root of 2, the numerical part for sure can't be simplified. X to the 6th would be essentially 2 triplets, right? X times X times X, another X times X times X. And then the cube root of y to the 4th is 1 triplet with 1 left over. And then they are the same. So we're in the same boat where the coefficients can't actually combine. So we just have to leave it as x to the second y plus 7 times the cube root of 2y. So we're going to add on just a little bit to the multiplying work that we've done in the last couple of days. The distributive property still applies. X times the square root of 3. And then the square root of 3 and the square root of 5 is the square root of 15. Still applies. Same thing here. Notice we only can do this multiplication because they are both cube roots. Remember that index has to be the same. So we get the cube root of y times y to the second plus the cube root of 2y. And as always, we need to look for any simplifying. So the cube root of y to the third is y. And then the second term can't be simplified at all. Multiplying binomials, you've done before as well. We can also do that with radicals. So 4 times the square root of 9. I'll deal with that in just a minute. If you can deal with that right now, totally fine. So first, let's see, outer 20 times the square root of 6, right? 5 times 4 on the outside, 3 times 2 on the inside. Inner square root of 6. And last, minus 5 times the square root of 4. So we end up with some whole numbers here. And some like terms that can combine. Negative 20 plus 1 is negative 19 times the square root of 6. And we end up with 2 minus 19 times the square root of 6. So I'm going to let you practice that next one if you want to. Go ahead and pause, and then you can check yourself. So we will look at this further in a couple of days, but there's a word. It's a conjugate. And their radical expressions, if you'll notice their relationship, is basically a plus b and a minus b. And we'll end up using them because if you multiply them, they end up not having some sort of radical term. If we multiply them together, our inner terms would cancel. And then when we do our first and our last terms, we end up with perfect squares. And so we're going to use that strategy in a couple of days. So hang on to that. So the one thing we need to go back, we did some multiplication the other day, and we talked about how the indices needed to be the same, right? Square roots with other square roots. However, if we don't have indices that are the same, we can put them into exponential notation, do some work, and then go back to radical notation. So for example, I recognize this first part as x to the 3 over 2 power over index and x to the 1/3. When I combine these together, I'm going to have common denominators because I'm going to be adding those exponents. So I'm going to go ahead and actually do that and get x to the 9/6 and x to the 2/6 so that then I can add those together more efficiently. And once we've combined them, right, we started with two factors that we were multiplying together, then we can go back to radical notation, the 6th root of x to the 11th, which has one set of 6 and 5 left over underneath your radical. If at this point you also recognize that you had 6th roots of x to the 9th, y to the 2nd, misread my own handwriting. So let's pretend for a moment we had a different problem. And if you had separate variables, right, you had different bases, totally fine. You could still at this point combine them, and then you'd be able to go further from there. The y to the 2nds, no, but for x to the 9th, you would. So even if you can't combine them at that point, you could still go back to radical notation as soon as they had that common denominator.